Let's consider how the notion of echelon form and reduced echelon form interacts with the notion of row equivalence. So let's see how Gauss's method acts. The following shows a sequence of transformations from matrices A in the left to B to C to D as shown. And we're going to view each matrix as a column of row vectors. So matrix A here has two rows. So here's the first row alpha 1, the second row alpha 2. So alpha 1 is the row vector 1, 3, 5. Alpha 2 is the row vector 2, 4, 8. And then we're going to take, here's the row operation, and we're going to view that from the point of view of forming linear combinations of these numbers. So, well, the beta 1 and beta 2 are the rows of B, and the first row doesn't change, so beta 1 equals alpha 1, but we add -2 times the first vector to the second vector. So this shows that B is the rows of B are actually linear combinations of the rows of A. So we continue with a rescaling, and that means that the rows of C are still linear combinations of the rows of A. Then we form another row operation here on the rows of C. And if we go through and see, well, we multiply -3 times the second row to the first row, what you end up with is that the rows of D are still rows of linear combinations of the rows of A. So this gives us an idea that Gauss's method acts by forming new linear combinations from the original linear combinations. Okay, so here's a summary of this idea. A linear combination which combines several linear combinations of variables, that's what was happening before, is itself a linear combination of those original variables. Here's the proof to gain an understanding of what this means. Let's consider a set of M linear combinations of n variables. That's the x's. So we have here like the first linear combination here. There's x1, x2, x3 up through xn with coefficients. And the 1 labels the linear combination. And so we're going to have like a second linear combination with a 2 there. And then this is up to the last one, the mth one, which has the same number of variables, but it has different coefficients. So now let's consider a linear combination of these linear combinations, lambda. So lambda, here's the coefficients of lambda, d1 times the first linear combination plus d2 times the second plus d sub m times the last linear combination. So this is a linear combination of linear combinations. Here the coefficients d are arbitrary constants, as are the coefficients for each of the original linear combinations. So what we're going to do is we're going to distribute the dn to each term in each of the terms, and then group all the coefficients of similar variables. So we're going to take like the d1 c1 1 times x1 and the d2 c2 1 x1 from the next one up to dm cm1. And so we'll collect all the coefficients of x1, collect all the coefficients of x2, of xn minus 1, and then xn. So this exhibits lambda as a linear combination of the original variables, which is what's claimed here. Okay, now here's a follow-up result. If one matrix reduces to a second via row operations, then each row of the second matrix is a linear combination of the rows of the first matrix. This just makes general what was seen in the example showing how Gauss's method acts. The book has the proof. Okay, now let's consider how this works for an echelon form matrix. The claim is, if a row of this matrix has non-zero entries, then it is not a linear, that row with non-zero entries is not a linear combination of the rows with non-zero entries. So the claim is, an echelon form matrix, you can't form a linear combination of one row from any of the others. Okay, let's see how this works. A proof by induction appears at the end of chapter 1, but let's look at the main idea with an example. Here's an echelon form matrix, 3 rows. Now let's consider writing the second row as a combination of the other 2 and see what goes wrong. Okay, so here's the middle row here, I'm going to write as a linear combination of some constant times the first row plus some constant times the third row. Is this possible? Well, let's see. You can see, I'll see right away there's going to be a problem, because if I just look at the first entries here, this is really this vector equation is really 4 numerical equations. In fact, this is a linear system. But you can see here, C3 times 0 plus C1 times 1 has to equal 0. Well, that's just this equation here. C3 times 0 plus C1 times 0 has to equal 0. Well, the only way this can be true is if C1 is 0. So we can't have C1 in the linear combination. Now let's consider the third row. The echelon form means that this number here has to be the right of the 5. So let's look at this first column here. Well, we already know that C1 times 2, the 0 from C1 means that the 2 doesn't contribute. So we're going to have C3 times 0 equals 5, which is a contradiction because 5 equals 0 is never true. Therefore, this linear combination is impossible, which confirms the lemma that because this is an echelon form, you can't write any of the rows as linear combinations of the other ones. So this is what Gauss's method does. Gauss's method forms linear combination of rows in order to systematically eliminate all linear relationships between those rows. Let's consider another example in this light. In the following matrix, the third row is the sum of the first and second, because you can see 1 plus 2 is 3, minus 1 plus 0 is minus 1, and 3 plus 4 is 7. Okay, here's the action of Gauss's method that reduces it to an echelon form matrix. So these are row equivalent. The only linear combination of the non-zero rows requires, well, there's only 2 non-zero rows. So the only way that there could be linear combinations here is if C1 times the first row equals C2 times the second row. And it's this equation here is going to end up forcing C1 and C2 to be 0, so we really don't have any way to make a linear combination. Let's just look at the first entries. Well, this is C1 times 1 equals C2 times 0, so C1 has to equal 0. Then we can look at the second entries. So we have, since C1 is 0, that's 0 equals 2 times C2, so C2 has to equal 0. So this shows how even though the original matrix had some linear relationships, that's been eliminated by Gauss's method. Now, how does the reduced row echelon form matrix fit in this if we continue through? This matrix is not in reduced row echelon form, so let's consider what happens if we go all the way and take an echelon form matrix to reduced row echelon form. And the book contains the proof, so let's try to understand it here. Each matrix is, the theorem is, the result is, each matrix is row equivalent, that's row connectable to a unique reduced echelon form matrix. That means that if you, no matter what pathway you take, no matter what row operations you perform, you're going to get to the same reduced echelon form matrix. This isn't true of just echelon form matrices. You can have different echelon form matrices, but you cannot have different reduced echelon form matrices. Let's see how this works with an example. There's the reduction here. You can see here, here's a matrix on the left, series of operations, and a reduced row echelon form over here. The theorem implies that the original left-hand matrix cannot be row equivalent to any of these matrices or any of the matrices that reduce to these by the same means. So that this matrix and this one are in different equivalence classes, row equivalence classes, than any of these three. Okay, so the way to summarize this is that the reduced echelon form matrix is a canonical form for row equivalence. That is, it's a unique matrix. There's only one matrix in each equivalence class, the reduced row echelon form matrix, that identifies that row equivalence class. So they can be used as representatives of the classes. This is very similar to what happens with fractions in a different context. You have 1/2, 2/4, 3/6, different fractions that all have the same numerical value, and we always take the fraction with no common factors. where you've reduced it to lowest common terms as sort of the representative of the matrix, of the fraction that is. Okay, so here's a picture of the situation. A star in each equivalence class, the star in each equivalence class represents the unique reduced row echelon form matrix in that class. This also gives an answer to the question, how can you tell if two matrices are row equivalent, that we asked in a previous video? The answer is reduce both matrices to reduced row echelon form. Then, if those forms are the same, the matrices are row equivalent. If not, they aren't. How can you decide if these two matrices are row equivalent? Well, we can use Gauss-Jordan elimination or reduction to bring each to reduced row echelon form and see if those reduced row echelon forms are the same. The results for the first, you get the matrix on the right, and for the second, you have a different matrix. Notice that the columns are the same, but the constants over here are different. So in fact, these are not row equivalent matrices. That's it.